I want to start this video with a quick reminder of our unit circle. This has a radius of 1, and our common angles. Here we have 0 degrees, which is equal to 0 radians. Then we have 30 degrees, which is pi over 6, 45 is pi over 4, 60 is pi over 3, and 90 is pi over 2. Once we move into quadrant 2, we'll have multiples of these. So we have 60 degrees once, 60 degrees twice will give us 120 degrees. 60 degrees 3 times is 180, and so on. The same principle holds for 30 and 45. So what we're going to do in this video is we're going to graph the sine function. Now, all we need to do here to graph anything, really, is to take the input values and graph the output values. So if I'm going to graph a function, f of t equals the sine of t, I need to identify first what the input values are and what the output values are. The input values are t's. Well, we've decided that we're calling our angles t. So my input values are 0, 30, 45, 60, and 90, or 0, pi over 6, pi over 4, pi over 3, and pi over 2. So let's make a table of values. I'm going to do that down here. T is 0, pi over 6, pi over 4, pi over 3, and pi over 2. So those are our input values. Our output values are the things that get spit out when we plug these into our function. Remember that the sine of t is the y-coordinate of a coordinate pair, right? So I can write this, the coordinates of this point right here as x comma y, or as cosine t comma sine t. So if I know what the y-coordinate is of any of these points, then I know the sine value. So for some of these, all we need to do is graph the y-coordinate. And here I can see that the y-coordinate is 0, right? This is the point 1 comma 0, so the y-coordinate is 0. I should put sine of t here, so we know what we're finding. Notice that these values are all in radians, so I don't have any degree symbols here because that's a different unit of measurement. And the other one that's really easy to find is the y-coordinate of this point up here. Here we're at the point 0 comma 1, so the y-coordinate there is 1, and that's at the angle pi over 2, so that value is 1 there. These others are less easy to find just in that we can't just pull them from the circle. Like I can't just look at this and see, oh, the x and y coordinates are, right? I don't know. But I do remember from my previous work what the x-y coordinate pairs were here from the unit circle diagram that we have labeled. So for example, the coordinate pair for 30 degrees is the square root of 3 over 2, comma, 1/2. The coordinate pair for 45 was 1 over root 2, comma, 1 over root 2. And for 60 degrees, it was 1/2, comma, root 3 over 2. Getting a little crowded in there. So all I need to do for sine is to go in and pull out the y values for each of these coordinate pairs. And I can put those in my table here. Let's see, 1 over root 2 and root 3 over 2. And with that, I now have input, output values, input, output, and I can use that to graph the function. So let's go ahead and plot some of these points. The point 0, 0 is quite easy to plot. I think I'll use a different color, let this stand out just a little bit. Let's use blue. I'm kind of in a blue mood. So there's the point 0, 0. As I go around, I'm going to notice, first of all, that by the time I get all the way around the circle, pulling various different points from the unit circle, by the time I've gone all the way around, if I were to make a second round, then all my values would be the same, right? Because the angles are coterminal to the angles in the first circuit of the unit circle. So I really only need to go around once from 0 to 360 degrees, or in the case of radians, 0 to 2 pi. And that's why I've labeled 2 pi as my kind of ending point here. This graph will actually go on forever, but I've stopped at 2 pi because I know that's how many times I need to go around. Equally, I know that the highest value I'll ever get for y is 1, right? The y value of this coordinate pair is 1/2. Scale's a little off here, but it's at 1/2. This one's at about 0.7. This one's at about 0.9. The y-coordinate of this point is at 1, but then they come down again. They never get any higher than that. The y-coordinate down here will be -1. So I can also scale my graph between 1 and -1 out there. All right, now let's get back to it. So I have a 0, 0 point here. Now I need the point pi over 6, 1/2. So where is pi over 6? Let's make some more marks on here. I've already put 2 pi on the t-axis. Halfway between 0 and 2 pi is pi. Halfway between those two is pi over 2. And here I have 3 pi over 2. Halfway between those is pi over 4. This one's going to be 3 pi over 4. Then I'm going to have 5 pi over 4 and 7 pi over 4. And I can find those values in the same way as I found the values in here, right? I have, for example, 1 pi over 3 here, a second one here that's 2 pi over 3, 3 pi over 3, that's pi, then 4 pi over 3, 5 pi over 3, and 6 pi over 3. I have 6 copies of pi over 3, that's 2 pi. So that's kind of how I'm breaking this down. If I do it with 45, if I do it with pi over 4, I have 1 pi over 4, 2 pi over 4s, that's pi over 2, 3 pi over 4, 4 pi over 4 is 5 pi over 4, 6 pi over 4 is 3 pi over 2, 7 pi over 4, and so on. Okay. Now, with the degrees, with the angles between, so far what I've labeled is the pi over 2's, right? Here, the quadrants, right? 0 pi over 2, 1 pi over 2, 2 pi over 2, which is pi, 3 pi over 2, and 4 pi over 2, which is 2 pi, and the 45's, the pi over 4's. But either side of pi over 4, there's a 30 and a 60, the pi over 6 and a pi over 3. So I need to put those in. I'm not going to label them because I'm running out of room. But do notice that they're not at halfway between the existing marks. They're closer to, they kind of hug the existing pi over 4 marks. So you kind of have to be careful when you're labeling your graph there. All right, now I can label or start to plot my points. I have 0, 0. My next one's going to be pi over 6, 1/2. So at the input value of pi over 6, which is just less than pi over 4, so just less than pi over 4, my output value is going to be 1/2. Well, I have 1 marked on my axis. Let's go ahead and label 1/2 as well. All right, and so I have pi over 6, 1/2 is a point right about there. The next one, pi over 4 for input, gives me an output of 1 over root 2, and that works out to be approximately 0.707. I'm just going to write 0.7 because that's as close as I'm going to get graphing anyway. My accuracy just won't be any better than that. While I'm at it, I'll give you an approximation for root 3 over 2. It's 0.866, about 0.866. We're going to call that 0.9, 0.9 for our graphing purposes. So now I have some output values I can plot there as well. When my input value is pi over 4, my output value is 0.7. So from here, I want to go up to about 0.7. That's 0.5. That's 1. So that's 0.75. So I'm going to be just shy of that. The next one is when my input is pi over 3. Right? That's the one that's just beyond pi over 4. So at pi over 3, my output is 0.9. There's 1/2. There's 1. I need to be just shy of 1. Okay, and my last one is when my input is pi over 2, my output is 1. So I'm right about there. So this part of the graph looks something like that. Now, I don't know if you've noticed this yet, but the graphs, the values that I've plotted so far have all come from quadrant 1. They've all come from angles, input values between 0 and pi over 2. So in here, I'm only working with input values between 0 and pi over 2. So I can kind of partition my graph here. This stuff, these values, this part of the graph all comes from quadrant 1. The next part is going to come from angles in quadrant 2. And that's going to take me for input values from pi over 2 to pi. So by the time I get to pi, I'll be finished with quadrant 2. Quadrant 3 goes to 3 pi over 2. Quadrant 4 goes to 2 pi. It's a very useful observation to make, so I just wanted to go ahead and stick that, put that out there for you to be aware of. Here are the next values that we need to use as our input values. Now, I'm not going to graph this whole function because we're going to run out of time. We really already have run out of time, and I still need to at least address the cosine function. So far, we're just dealing with sine. So what we need to do here is recognize what our reference angles are. For example, the reference angle for 2 pi over 3 is pi over 3. So when I add to my chart, which I'll do right now, in order, we've already got to pi over 2. The next one we need to graph is the value for 2 pi over 3, then 3 pi over 4, then 5 pi over 6, and then pi. But the reference angle for 2 pi over 3 is pi over 3. So I'm going to get the same output value, pi over 3. Let's see, where am I? For pi over 3 gave me an output value of root 3 over 2. And y values are positive in the second quadrant, so it's going to stay 3 pi over 2. To graph or to find the output value for 3 pi over 4, I need to first find the reference angle for 3 pi over 4, and that's pi over 4. Right? This angle right here is the same size as this angle right here. So the output value will be numerically the same, pi over 4. I'm going to have 1 over root 2. I'll call it pen. 1 over root 2, which is about 0.7. I'll put about 0.9 here for us. And then for 5 pi over 6, we have a pi over 6 reference angle. So our pi over 6 reference angle is here. Our pi over 6 reference angle's output value is a half. Okay. And our y value for pi, which I don't have on here, our y value for pi is 0 again. So I can now graph these input-output values for 2 pi over 3. I have 0.9, so I'm back at about this height here. Notice that that matches the height here. Then at 3 pi over 4, I'm at 0.7. So I'm going to be about here. And then at 5 pi over 6, I'm at a half. And then at pi, I'm at 0. So this part of this graph looks something like this. A little squiggly in there. It shouldn't be so squiggly. All right. In the next quadrant, we're going to have the same thing again is going to happen. If I extend my chart here, and I have my next input value, which would be 7 pi over 6, then my output value is going to be the same as the reference angle pi over 6, 1/2. Okay. But in this quadrant, y values are negative, so now it's going to be negative a half. So when I plot that point, I'm going to be at 7 pi over 6, which is right here, and at negative 1/2, which is about there. So the graph will continue down here like this. That's all I'm going to do here because number 1, you can find this graph in your textbook. Number 2, we can finish it in class. I don't want to take any more time to do this. And number 3, I want to at least address graphing the cosine function. So if I erase the f of t equals sine of t and replace it with cosine of t, then I've also erased all my output values down here. I'm going to remind us that what we're graphing is the cosine of t. I'm not going to do as much with this graph, with this function, as I did with sine, because again, we're over time and I want to save some things to do in class. So here what I want to do is, again, take wherever I can, take y, in this case, sorry, x values, cosine is the x value, take x values from the graph, right? So the x value, when the input value is 0, when the angle is 0 radians, the output value is whatever the x coordinate is in this case. So the x coordinate here is 1. So at input of 0, the output is 1. The x coordinate here is 0. So at pi over 2, I have 0. At pi, I have -1. My output here is an x coordinate, which is -1. So those are the easy ones. And then the others come, again, from what are the x coordinates for 30, 45, and 60, or pi over 6, pi over 4, pi over 3, and so on. And that's root 3 over 2, 1 over root 2, and 1/2. So let's put those in. Root 3 over 2, 1 over root 2, and 1/2. And remembering that root 3 over 2 is approximately 0.9, 1 over root 2 is approximately 0.7. I can graph these first, I can graph the first quadrant. All right, so I have 0, 1, which goes here. Then I have pi over 6. Remember, pi over 6 isn't labeled. It's this guy right here. It's right before pi over 4. So it's right before pi over 4 on the unit circle. It's right before pi over 4 in the graph. I need about 0.9. Well, at pi over 6, there's 1. I want to be just shy of that. So there's 0.9. And then at pi over 4, I'm above 0.5, but below 0.75. So right about there. And then my next value is at pi over 3, I'm at 1/2. So that's about there. And at pi over 2, I'm at 0. So this part of the graph looks something like this. Okay, continuing. I'm going pretty quickly now because I want to make sure that we have time to do all of this. I'm going into quadrant 2 now. So I'm looking at x coordinates here. So my x coordinate for 2 pi over 3, here's my reference angle, is going to be the same as my x coordinate for pi over 3. What was my x coordinate for pi over 3? 1/2. So I'll go ahead and write in 1/2. But the thing to notice here is that all my x coordinates in quadrant 2, all my x coordinates are negative, right? So that's going to have to be -1/2. And in fact, all the way through quadrant 2, my x coordinates are negative. And in quadrant 3, my x coordinates are negative. So these are all going to be negative, right? One more, and then I'll call it quits for this video. 3 pi over 4. At 3 pi over 4, my reference angle is pi over 4. So I'll go find pi over 4, and I have 1 over root 2. 1 over root 2, but because I'm in quadrant 2, it's negative, and that's approximately -0.7. The next one's going to be approximately -0.9, and so on. I'll graph those very quickly. I have -1/2, about there, -0.7, which is about there, -0.9, which is about there, and then -1. So this part of this graph looks something like, I didn't quite get my points matched up there, looks something like that. So there you have quadrants 1 and 2 for the cosine graph as well. All right, because I know this graph, and because I want to have at least one copy of one graph so that we can talk about the last concept in this video, I'm going to go ahead and finish this graph. And I'm going to 1/2, 0.7, 0.9, and 1. Not sure I quite got there. But the entire graph looks like this. Now, when I say the entire graph, and this is the reason I actually finished this graph, this is not the entire graph. Because if I start at theta equals 0, sorry, at t equals 0 and go through t equals 2 pi, I get this. But I could go around again and again and again. So this graph actually repeats forever. This is only one cycle of this graph. In fact, if I started at 0, I could go backwards. So this graph also goes in this direction forever. So this is actually just one cycle of a graph that goes on forever and ever and ever. This is what this one cycle, we call this a period. A period is the length of the part of the t-axis, right, the input value axis. That's how long across the t-axis it takes you to go through one entire cycle before you would have to start over, right? Now, if we did started another cycle here, this graph would go back down and repeat this pattern, right? But we're going to stop here only because we recognize that we've gone all the way around the circle. So we've gone all the way through one cycle. Another cycle would just repeat the pattern. So that cycle, or the amount of time it takes to complete that cycle, is called a period. The amount of time, the amount of t-axis it takes up. So with that, I can say that the period of cosine is 2 pi. That's how long it takes to go through one cycle. It takes this much space to go through one cycle of cosine. There's really no way to have made this video any shorter, and trust me, I tried. I've actually restarted it 3 times. So I apologize for its length, but we're going to quit there, and there are a couple of others to do in this section, so you'll see videos following this one. And the rest of this we'll cover in class. There's not a whole lot more. We'll investigate completing the graphs in class. But right now we're going to move on to investigating sinusoidal functions.